For about 15 years now, off and on, I've had to work with Bayesian algorithms and compute Bayesian probabilities. Not enough to be the world's foremost expert or anything like that, but enough to realize how freaking useful it is in the real world. Not to sit down and do math, but informally, in your head, the concepts behind Bayes' theorem are so useful in evaluating scientific claims, political claims, product advertising, and so many other cases when traditional thinking, and even traditional skeptical thinking, might lead you astray. Understanding this well enough to at least informally keep it in the back of your mind can completely change the way you view the universe. In this video, we'll see the simple equation that will change your life. I've noticed that even skeptics have a problem with probability. The human brain just isn't set up for it. But actually, most skeptics are probably halfway there. So I'm making this video to try and explain it the rest of the way, so that if you're familiar with skeptical thought, you will be in a much better position to evaluate various claims and incorporate new evidence into your view of the world around you. First, let's talk about how probability is expressed mathematically. Probability is expressed as a number between 0 and 1, with however many decimal places you might need. So the chance of a fair coin flipping heads is 50%, or 0.5. That 1 in a million chance is 0.000001. And if something is 99 and 44/100% sure, its probability is 0.9944. Probability is the basis for Bayes' theorem. Here it is. As you can see, it's a bunch of gobbledygook, so we're not going to worry about that. We're going to take a look at a specific problem, and then take a look at the math and see how we can do this informally, even internally. Let's say you're an oncologist, and you're giving a patient a mammogram. If she has breast cancer, then your machine has a 90% probability of showing a positive result, meaning 10% of the time it'll give a false negative. If she doesn't have breast cancer, there's a 7% chance of a false positive. Your patient gets a positive result for breast cancer. What is the probability that she actually has breast cancer? Ballpark figure is fine. Just take a minute and give it a think. So what did you say? Does she have a 90% chance of having breast cancer? Oh, but there's that 7% false positive. What does that do to things? Do we subtract that and make it 83%? What is the proper answer? Actually, the proper answer is you don't have enough information, because you also need to know what the probability is that she even has breast cancer in the first place. This is called prior probability. If you're a skeptic, you're familiar with this concept already. Extraordinary claims require extraordinary evidence. That saying is what prior probability is all about. If you just went with the evidence, then you don't know how strong the evidence needs to be to overcome prior probability. If you're reasonably sure of something, you don't need much evidence to put it over the top. But if it's very unlikely, you need a lot more. Let's say your friend sees a UFO. He says it's a spaceship. You predict a more terrestrial explanation. Maybe he misidentified a plane, or the moon, or a local wedding sent up a bunch of Chinese lanterns. The prior probability of your hypothesis is very high. The prior probability of his hypothesis is very low. So the evidence for his hypothesis needs to be stronger than yours. If you read in the paper that there was indeed a wedding that day, and you ask around and find out that they did release sky lanterns, that's probably enough. Your prior probability is high enough that this information alone is enough to put your hypothesis over the top. But if you read that someone else saw a UFO that night, and ask around and a few others did too, then, even though it's essentially the same kind of evidence that you have, a newspaper report plus eyewitness testimony, it still isn't anywhere near enough to confirm his hypothesis, because that level of evidence isn't even close to what is needed to cover the extremely low prior probability of space aliens. So when you give your patient that mammogram, you need to know what the chances are that she has cancer to begin with. And you might base this on a lot of things. Is she in there for a routine screening, or is there some other reason to believe she might have it? How old is she, and how prevalent is breast cancer in her age group? Does she have a family history or other genetic indicator putting her at risk? So let's give her a prior probability of 0.8%. A 1/8 of 1% chance that she has breast cancer. and put it in our problem. Remember, your test has a 10% chance of a false negative and a 7% chance of a false positive. Now take a minute and think about it again. Got a ballpark figure in mind? Okay, now I'm going to give you one more piece of information. A cognitive psychologist at the Max Planck Institute gave this exact word problem to 25 German doctors and 100 American doctors. 90% of them got the answer way wrong. So this problem is so difficult that it even trips up professionals. Armed with that information, maybe you should give it another minute and rethink it. Okay, now let's use a Bayesian calculation to find out if you're right. I put a Bayesian calculator in the video info box. Make sure you have JavaScript turned on. Plug these numbers in. First, make sure you've selected probability and not odds. We'll get to odds in a little bit. P of H is the prior probability. That's 0.8%, but remember, we need to express this as a number between 0 and 1, so that's actually 0.008. Place that in the first text block. The next block is P of D given H, or the probability of the data given the hypothesis. This is how likely you are to get a positive result if your patient has cancer. In our problem, that's 90%, or 0.9. Put that in the second block. The next line, P of D given H prime, is the probability of a positive result if the patient does not have cancer. In other words, a false positive. That was 7%, or 0.07. Place that text in the third block. Now for the moment of truth. Think about the answer you had in mind. Was it 90%? 83%? Maybe you went as low as 50%, or even 20%. Or does that sound too low? Go ahead and click compute and let's see how well you did. The real answer is less than 10%, meaning that there's over a 90% chance that this is a false positive. Does that surprise you? This is how much the prior probability matters. Yes, that 7% chance of a false positive is pretty small, but what you have to understand is that it's 7% of a much larger group. Let's say we give this test to 100,000 such women. We know, thanks to the prior probability, that 800 of them have breast cancer. We give them mammograms. Of the 800 that have breast cancer, 90% of them will test positive, or 720. The other 80 will show up negative even though they do have breast cancer. That leaves the 99,200 that don't have breast cancer. Of those, only 7% will test positive, but since it's 7% of this much larger group, we can expect 6,944 of them to experience false positives. So the total number of positive test results we have is 6,944 plus 720, or 7,664. Since only 720 of those actually have breast cancer, then the probability of a positive test result, meaning the patient has cancer, is 720 over 7,664, or 0.0939 and change, or about 9.4%. So despite this positive result, our patient is much more likely not to have breast cancer. Now that doesn't mean that the test was worthless. Remember, before the test, we were only 0.8% sure, and now we're up over 9%. So it's an improvement, but I think this sufficiently illustrates the problems that can happen when this kind of probability is misunderstood. So now that we've taken a look at the problem, let's see if we can find an easy way, not to calculate it necessarily, but at least to infer it in our minds. To do this, we'll use an easier form of the equation, which uses odds instead of probability. Let's go back to our fair coin. Its probability of coming up heads is 0.5, and consequently, its probability of coming up tails is 0.5, which means that the odds of it coming up heads are 1 to 1. A ratio is division, and 1 divided by 1 is 1, so we can also simply say that the odds are 1. Mathematically, it's easy to compute odds. P over 1 minus P. So in this case, it's 0.5 over 1 minus 0.5, which is 0.5 over 0.5, which equals 1. In our scenario, the probability of a woman having breast cancer is 0.8%. So the odds of her having breast cancer are 0.008 over 1 minus 0.008, or 0.008 over 0.992, or 0.008064516 and change. When we use odds instead of probability, we can easily see a very important concept in Bayesian algorithms. It is not permissible to have a probability of 1, which would be an absolute certainty. Try and convert it to odds and you'll see why. 1 over 1 minus 1 means dividing by 0, which isn't allowed. It's also worthwhile to mention what are called log odds. This is the natural log of the odds. Since the natural log of 1 is 0, then 0 is an even chance. Positive log odds are better than even, and negative log odds are worse than even. Log odds lets us understand the next principle. Just as you aren't allowed to have a probability of 1, it's not possible to have a probability of 0 either, or an absolute impossibility. A probability of 0 means odds of 0. But the natural log of 0 is an absurdity. The reason why is that to calculate the natural log, you raise e, the natural log base, to the power of x, and set that equal to your odds, then solve for x. But there is no number which you can raise e to the power of, which will give you a result of 0. As a skeptic, this should appeal to you as a feature, not a bug. Nothing is ever 100% certain. There should always be a certain amount of evidence, however huge it has to be, that can prove you wrong. Consequently, no matter how convinced you are that something might be impossible, there should always be a certain amount of evidence, again, however huge it has to be, that will get you to take it seriously. Now, if you think of things in terms of odds, Bayes' theorem becomes a lot more simple. It's just the prior odds multiplied by what's called the likelihood ratio, also known as the Bayes factor. In a medical context, it's often known as diagnosticity. This is the probability of the evidence given the hypothesis divided by the probability of seeing the evidence if the hypothesis is untrue. Don't get confused here. The likelihood ratio is not the ratio of the evidence for to the evidence against. It's the likelihood that you would see this particular set of evidence if the hypothesis were true, divided by the likelihood that you would still see that very same set of evidence if the hypothesis were false. This is Bayes' rule. Posterior odds equals prior odds times the likelihood ratio. And once you understand this relatively simple equation, it will change your life. So going back to our problem, with a 90% probability of a true positive divided by a 7% probability of a false positive, the likelihood ratio becomes 12.857 and change. We computed the odds earlier, multiplied the two, and the odds of our patient having cancer becomes 0.10368, etc., or about 1 in 9.65. But let's say that, instead of using a mammogram, we flip that fair coin. Heads, she has cancer, tails, she doesn't. The probability of getting a positive result if she has cancer is 0.5, but so is the probability of getting a positive result if she doesn't have cancer. That makes for a likelihood ratio of 1, which means multiplying that by our prior odds doesn't do us any good. We're left with the same odds as we started out with. Really, the relationship is the important thing. If you can get a general idea of the odds, and you can get the likelihood ratio into your head, you can get a pretty good idea of how much you should believe the hypothesis given the evidence. Now, the important thing is not to try to get some kind of number here. The point is it forces you to go through the mental process. Consider the prior odds, and extraordinary claims require extraordinary evidence. Consider how strongly the evidence supports the hypothesis, not only by considering how likely we are to see the evidence if the hypothesis were true, but also how likely it would be even if the hypothesis were untrue, and get that all-important likelihood ratio. One common mistake is to take the probability of the evidence given the hypothesis, which is one of the elements you're considering, the numerator of the likelihood ratio, and confuse it with the probability of the hypothesis given the evidence, which is the result of the Bayesian calculation, what you're trying to figure out. So don't go thinking that a 10% chance of a false negative means she has a 90% chance of having cancer. It doesn't. That's confusing P of D given H with P of H given D. By the way, you might very well run into a scenario where the likelihood ratio is the same for two different and mutually exclusive hypotheses. Of course, here, the prior odds become the determining factor. And now we have an expression of another concept well known by skeptics, Occam's razor. William of Occam said, never posit plurality without necessity, or in other words, don't bring in anything you don't need to explain the phenomenon. It's a razor that shaves away unnecessary assumptions. In more modern usage, it's considered to mean something like this. If you have two hypotheses which are explained by the evidence equally well, the simplest one is usually correct. But now, here, we have it embedded in Bayes' theorem, and we can state it thusly. If the evidences for multiple hypotheses have equivalent likelihood ratios, go with the one that has the highest prior odds. Really, that's all Occam's razor is saying. Here's something else skeptics should be able to identify with, the false equivalence fallacy. Creationism deserves equal time with evolution and so on. But it just doesn't. And the reason why is that creationism has a much lower prior probability than evolution. 150 years of evidence has increased evolution's odds so much that, despite the fact that we aren't allowed to be infinitely certain, we have more than enough to be pragmatically certain. The two ideas are not on equal footing. Now, one of the things this channel has become focused on in recent years is to get people thinking critically about political issues, and as we've seen repeatedly, even skeptics have a huge deficit here. In America, most people involved in politics take sides in the political game based on a mythical left versus right dichotomy, with most skeptics taking the side of the left. And just like the fans of two different sports teams, just like the worshippers of two different religions, each side takes the position their side advocates and the other side opposes. And any voice of rationality gets shut down as one of the other guys, the not we. It's just human nature. To survive for so long, early humans and their non-human ancestors had to band together for survival. So you may become a member of the we, and any not we is an enemy to be opposed, or at least somewhat distrusted. So the one thing you did not want to do is let the other members of your group think of you as not we. That could get you killed. One of the goals of the Enlightenment has been to get people to encompass all of humanity in the we so that there are no human beings who are not we. But that idea has only been around a couple of centuries, not enough time for evolution to have an effect. So we still have the tendency to fall into this pattern. I'm part of the we, and anyone different is not we. It's one thing when it's a sports team. It's something else entirely when you're talking politics and electing people and giving them the power to use force against us. I've been called right-wing by leftists and left-wing by rightists. When you're in this position, it's easy to see the absurdity. Not so easy if you're going along with the we. And I get this treatment from skeptics all the time. All they do is call me a right-wing nut or a teabagger or whatever zombie term they mindlessly throw out. They might say, you hate the poor, or you don't care about children. These terms and phrases really only exist so the person will have an excuse not to think about the issue. Their opponent is part of the not we, so they can be easily dismissed. The costs of their policies get ignored, as do the benefits of the policies of the not we. But once your mind goes Bayesian, it becomes a bit harder to do. It's like you have a tiny little Thomas Bayes inside you, like Jiminy Cricket, trying to keep you from going astray. One big question to keep in mind is simply, what does your belief not allow to happen? Here's one we've encountered in recent years. Obama's much-touted stimulus doesn't seem to have had the intended effect on the economy. What do the supporters of stimulus, even many skeptics, say is the reason? Because we didn't spend enough money. I think there's no doubt that if the economy did get reasonably better, they'd be saying, see, it worked. But the economy's either going to get better or it's not. If you truly wish to be rational, then there must be something that could conceivably happen to prove you wrong. That's what it means to make a prediction. But if you have answers to every conceivable result, you haven't made a prediction at all. And I'm sorry, but saying ahead of time, gee, I don't think it'll be enough, does not count as a prediction. All it does is expose your duplicity, because deep down, you know your idea is bogus and you're trying to set up your excuse ahead of time. A theory that explains everything, in reality, explains nothing. How likely is it that the economy would have recovered within a year or two? That's generally what happens when government is hands-off, so this extended recovery is an anomaly. It's far more likely that the stimulus delayed the recovery than it is that the recovery was delayed despite the stimulus. Really, the economy should have recovered long before now, so the likelihood ratio of the current economic conditions is a high probability it was caused by the stimulus divided by a low probability that it would have happened anyway. So keep that all-important likelihood ratio in mind, and whatever you do, don't forget the denominator. By focusing on probability, Bayesian thinking really lets us know that our view of reality is simply a map, which may or may not correspond accurately with the territory. Bayesian inference is a way of making that map more accurate. And it doesn't matter what the herd is doing or how much you don't like what the not we has to say. I've even had skeptics tell me that the concepts of rational inquiry just don't apply to politics or economics, or that government, just a group of people, has abilities no other group of people could possibly have. Fair warning, once your mind goes Bayesian, there's no going back. Special pleading, or herd thinking, or dismissing the not we just doesn't have the same effect that it once did. And that's a good thing. So if you have issues with anything I've said in this video, it's vitally important that you stop and ask yourself if you're really the skeptic you thought you were, the skeptic you want to be. And if you find yourself confident and assured that you are, then there's one more thing you need to understand. A true Bayesian wouldn't be.